find ways of truthifying it to make it work. This idea about unification would have put electrons on the same footing as quarks. Electrons have electric charge, quarks have color charge, and if color and electric charges are really the same, they're actually the same thing, different sides of the same dodecahedron, so to speak, and similarly for photons and gluons. So we'd get that tremendous unification with the SO10, which was the force carriers, and the big table of particles, which was the electrons and quarks. But this still leaves two kinds of matter, and two is more than one. So we can try to up the ante. Can we do this? Now, to a physicist, this actually seems quite shocking. It may not seem very shocking to you, but if you knew, the more you know about physics up to a point, the more shocking it seems to try to claim that electrons and photons are the same kind of matter. Electrons famously obey the Pauli exclusion principle. They don't like to do the same thing. They don't like to occupy the same quantum state. That's why matter is hard, even though we know that atoms are mostly empty space, but the electrons don't want to be too close together. Whereas photons love to do the same thing. That's why when you have lasers, you can get many, many photons in light to be doing exactly the same thing and organize themselves into nice beams that are what's called coherent light. So this proposal seems like trying to unify apples and oranges. There should be apples and oranges here. Let's get to the apples and oranges. Oh, I'm sorry. Okay, I'll have to do it in a different way. We can do this, however, and I'll get to the apples and oranges in due course. We can do this if we postulate something called supersymmetry, which is an expansion of the equations of physics that gives more structure, again, like adding more pieces to the more missing pieces to the dodecahedron, so that it can be rotated in additional ways, in this case, ways that allow electrons to change into photons and being seen as different facets of the same object. Doing that, however, supplying these extra pieces means we have more stuff. And remember, everything that exists in reality also exists in this fluctuating form, also changes the properties of empty space, and therefore means we have to make different corrections. And if we add in the particles that are necessary to make supersymmetry work and make those corrections, instead of that near miss I showed you, when we calculate with the asterisk, meaning we include the virtual supersymmetric particles, they come together. Triple exclamation point. Within the experimental accuracy, which is basically the width of these lines. So this unification idea, which seems so compelling, works if and only if we up the ante by demanding not only unification of the different forces, but also unification of the different kinds of matter. It seems like unifying apples and oranges. That's a very tricky thing to do. But the way it can be done is to postulate an extra dimension of space, not one of these crude dimensions that you could move around in. This is a quantum dimension, so you can't jump into it and explore. What happens to you if you move into this extra quantum dimension is that you turn into another kind of particle. If you were a boson, you turn into, if you were a boson, a photon-like particle, you turn into an electron-like particle. If you were an electron-like particle, you turn into a photon-like particle. That's what happens when you move into this extra quantum dimension. So if such a dimension exists, it means that for every particle we know about today, there's what you get from it by moving into the extra quantum dimension, its so-called superpartner, which will have mostly the same properties. Will have the same electric charge, the same color charges, the same strong, weak, and electromagnetic interactions. Will differ, however, in being a boson instead of a fermion, or a fermion instead of a boson, and in its how much spin it has. So it will differ in certain details, but mostly the same. And it'll be heavier. Anyway, it has predictable properties. So given that we know about electrons, we predict a new kind of particle, which is its super partner. What happens when an electron pops into the quantum dimension? It becomes a selectron, which is heavier and has precisely predicted properties. If a photon moves in to the quantum dimension, it becomes a photino. We have silly names for all these things. So there are gluinos, there are Higgsinos for the Higgs particle, and so on. A lot of extra stuff. It's all boiling, like those gluons I showed you, and we have to correct for all of it, and when we do that, the unification works out beautifully. We've learned the mathematics that changes our dimension into this quantum dimension, allows us to move freely between them. And so now we know how to, by maneuvering in an extra dimension, change apples into oranges. It's really easy. You just have to move in a quantum dimension, and it's fun. You can do it. It becomes a compulsion after a while. So, supersymmetry brings in new fluctuations, new corrections. That's the good news. We needed them. They help us with unification. Here's a more quantitative version of the same thing. And there's a bonus. So far, I've put gravity to the side. Let's bring it in, see if it too fits. Wouldn't that be marvelous? But gosh, that seems hopeless when you first look at it. The difference in strengths between the strong and weak force, for example, in this plot is roughly like a factor of 5, and then there's another factor of 2 or 3 to go to the electric force. So they're roughly, not grossly, not terribly different. Suppose we tried to put gravity on this same plot. Where would it be? Well, gravity acting between fundamental forces, fundamental particles, which are really small, have really small mass, is a much, much weaker, ridiculously weaker than the other forces. So is it 10 times weaker, so you get to the ceiling here? No, that's not enough. How about 10 times 10 weaker? So you get to the lower atmosphere and maybe hit a stealth bomber or something. No, that's in the right direction, but it's not enough. How about 10 times 10 times 10? So you get to the upper atmosphere. Nope. Keep going. 10 times. You go to the moon. You go to the outside of the solar system. Still not enough. Gravity is so much weaker than the other forces. It would take 40 powers of 10 to get to gravity, which takes you way, way, way outside the known universe. So actually, I did plot it here, but you can't see. However, we have to ask, we've learned from our unification that we really can only expect unification at much shorter distances or much shorter energies, much larger energies, so we have to see what gravity does at much shorter distances, much higher energies. And I've done that calculation. Here it comes. So from way outside the known universe, gravity roars in at the last moment and also comes to unify with the other interactions. This didn't have to happen. It's a marvelous surprise,